All right, we've made it to cancer module number 3. So here we're actually going to look at vehicle. We're going to look at the lowest dose, a middle dose, and a high dose. So this is going to be a rather complicated analysis, right? Again, we're going to be using a lot of the binomial distributions and a lot of beta distributions. So just to quickly remind you, in case it's been a while since you've been looking at this, in every one of these cases, we have the ideal case of having the same number of animals. For our purposes here, it could be different and it wouldn't really matter a whole lot. But for like frequent statistics, that could actually become a bit of a challenge. So let's get into the details of these particular analyses. We've got 60 animals in each one of the groups. Again, in vehicle, you've seen this several times now. We've got 5 animals that develop tumors. In the low dose group, we have 8 animals that develop tumors. In the middle dose, we have 7. And this happens, right? And the high dose, we've got 20. So we've looked at the vehicle before, we've looked at the high dose before, and now we've got this lowest and this middle. Because we're in a situation where we could have multiple testing, we need to make sure we correct for that somehow. Well, in the literature, there's a pretty good theoretical basis that we could actually just use a hierarchical Bayes model, and that will take care of the multiple testing issue. And we'll go into what exactly the hierarchical Bayes does in a few minutes, but this is mostly one of those nice things about using a Bayesian approach is we don't have to worry so much about that whole multiple testing thing when we are using a hierarchical Bayes model. So, to review, the objectives or the questions that we're trying to answer, the first one is, again, what is the probability? But in this case, it's that the low, middle, and high doses develop tumors. So we'll be calculating that. And then the question that we really care about from a risk assessment standpoint, are there differences in the probability of tumor formation in the low, middle, or high doses when compared to the vehicle? So, in order to answer that question, we got to answer the first question. Now, this module, module number 3, builds on what we've already learned so far. And like I say here in the text, there's a new twist. And that new twist is the hierarchical model. So let's talk a little bit more about the hierarchical model. When would you use this thing? Well, hierarchical models are really nice for things that we encounter in toxicology all the time. Something we call nesting or hierarchical structures in the study design. And now you might be familiar with this term nesting. If you're not, let's go through it real quick. So nesting is this concept where you've got some samples, but they are grouped by some higher order thing. So that was a really crappy definition. So let me give you some examples that will hopefully illuminate this a little better. When I think of nesting, the easiest thing for me to think of is, well, I worked with some folks who were at the USGS and they studied bird eggs. And bird eggs occur in a nest, right? This is why this is such a fun example. So they would sample from these bird eggs, and they're trying to measure who knows what, but they're trying to measure something. Let's say probability that the egg turns out to be a male or a female is probably one of the easiest things for us to think about. So they're going to sample these eggs. They're going to take some genetic material, and the thing is, those eggs all occur within a nest. That nest is a very specific environment for them. So when we go to do the analysis, if there are 5 eggs in the nest and they sampled from all 5 eggs, the treatment is actually technically at the level of either mom or the nest environment. So we don't typically have an N of 5 from a single nest. We have an N of 1. Because the experimental unit, the thing that actually got the exposure or the experimental treatment, is not the individual eggs, but it was actually the nest or mom. Another example that we like to use is animals in a cage. So if you've got all your vehicle animals in one single cage, all those animals together in that cage are sharing an environment. And when we go to look at, well, what received the treatment? Was it the individual animals? Well, technically, yes. But because all the animals in that cage received the same treatment, statistically, that means that the cage is the treatment unit, or what we call the experimental unit. And so therefore, in that case, you again have an N of 1 for your vehicle. Now you might be saying, wait, this sounds horrible. I'm losing all my N just because I happen to do something out of convenience, which is assign a treatment to a cage. This is absolutely ridiculous. And I'm going to tell you, yeah, kind of it is, but that these animals that are all in the same cage, or these animals that are nested together, unfortunately are correlated together. And that correlation is what is going to end up driving a lot of the variability, which we want to be able to separate from the treatment, but we can't. So what we need to do in the study design is we need to account for this nesting. Now, let's say you had 2 cages of vehicles. Well, now we're doing a little bit better, or 3 cages of vehicles. Okay, now we're getting to the point where I could probably use math to get out this vehicle effect or this nesting effect. And that's really what that's a great reason to use a hierarchical model, is because we can actually represent the actual study design that was used in our model. Now, folks doing in vitro studies, you're not safe from this. In fact, typically most in vitro studies have tons of nesting. And this isn't really a subject that's talked about much in vitro. Same thing in ecology. This isn't something that gets talked about a lot in ecology. So in vitro, I got bad news for you. If you have a 6-well dish and you devote 3 wells in that dish to vehicle and 3 to treatment, it's very convenient. That's really good. But now those samples are nested within the dish. And the only way for us to be able to figure out what the dish effect is on vehicle and on treatment, which, by the way, the dish effect can be different for vehicle and different for treatment. Just keep that in mind. But we can get rid of that plate effect if we have additional plates that have the same kind of arrangement. 3 vehicles and 3 treatments. If we have multiple dishes like that, or multiple plates like that, now we can start to calculate a dish or a plate effect. Same thing goes for mediums, for your media that you use. Same thing goes for your lots of serum, which, hopefully you're not crossing serum lots without doing extensive testing to make sure it doesn't cause any issues. We talked about the pregnant animal thing. But here in this section here, I'm giving you lots of concrete examples of where we see this. If you're one of the people who likes to use ToxCast and Tox21, whoo boy, man, I feel for you. I really do, because you're dealing with a lot of nesting in those ToxCast and Tox21 assays. And so, yeah, that's going to be a subject for another day. Not in this course. There's going to be a whole course I've got planned, if there's enough interest, focused just on Tox21 ToxCast, because whoo doggies, it's gonna be crazy. I tell you what. Whew. So anyway, the good news is hierarchical models can control for some of these nesting and hierarchical effects that are in the study designs if you know about them. Sometimes we don't know about them, and that'll come back and bite us in the butt later. And 2, we have to have the proper levels of replication to be able to take them out. So, there's all that kind of stuff we got to work with. Anyway, That's what the hierarchical model is all about. We're going to talk in a couple minutes about what that all means practically for you. But before we get there, I just want to show you what this looks like in practice in the stand file. So you're going to see that the stand file looks a little bit different. I have extensive commenting in here to help you wrap your head around what we're doing in the stand file to represent the nesting. This kind of, I'll be honest with you, this is a little bit trickier than what we saw in Module 1 and Module 2. It's not that bad. So I'm going to try to walk you through this, and you may need to go through this a couple times. Stop and think about it as you go through. And you should be doing that anyway. Anytime you're looking at code, you should always stop and think about what does every line of code mean. And hopefully I've documented this well enough that you'll be able to pick it up on the first, second, third, maybe fourth time, because this is kind of tricky. So as always with stand file, we're going to start the data block. Because of all my extensive commenting, the data block starts at line 21. So here, starting at line 5, I talk about what is happening here in this data block. So the first thing we have is we've got this variable or object called J. And here in the inline documentation, I say this is the number of studies. In this case, it's the dose groups, including vehicle. So we've got, let's say, low, we got medium, we got high, we got vehicle. So that's a total of 4 groups. So when we go to build the data within the RMD file, you're going to see J equal to 4. So we're assigning the value 4 to J because there are 4 groups, or quote unquote studies. You can't see the air quotes I'm doing with my hands, but studies. All right. So, and that's what this is explaining here. This is saying, the J part means that N is, well, yeah, there we go. I jumped, didn't I? Okay, so J is number of studies or dose groups. Okay, now we're going to look at N bracket J. This is a new notation for us. I don't think we've talked about this notation before. What this means is we're going to have a vector called N that has J number of slots in it. So remember, we just discussed J is going to be 4. So the vector N is going to have 4 wooden blocks in it. Okay, remember if we were talking about vectors before, and vectors have slots, or we can think of them as wooden blocks, right? So there's going to be 4 of them in here. That N is the number of experiments. So this is actually going to be 4 wooden blocks in a row that say 60. So 60, 60, 60, 60. And let's go over to this file here. Here's where we're actually building out the data that goes into the data block. And you can see I mentioned before J equals 4. And then we're going to have 60 minus 1, 60 minus 1, 60 minus 1, 60 minus 1. This is vehicle here, low, medium, high. And we're going to keep that ordering as we go through. So it's always going to be vehicle, low, medium, high. You could be evil if you wanted and change it and say, this will be vehicle, this will be high, this will be low, this will be medium. But don't do that because 1, it's confusing, and 2, it's just plain evil. Don't do that. That's just mean. Okay. So, and again, I explained the fact that I don't use the words evil, but I do say that you got to keep them in the same order throughout whenever we do things. So for YJ, it has to be in the same order as for NJ. You'll remember YJ now is going to be a vector similar to NJ. It's got 4 slots, except Y is the number of successes. So again, slot 1 is for vehicle, 2 is for low dose, 3 is for middle dose, 4 is for high dose. And coming back over here, we can see for vehicle, we had 5 successes. We had 8 here, 7 here, and 20 here. And again, we're subtracting 1 because of the silliness that Stan uses when it does binomial and binomial distributions. All right, so that's the data block. Now we're going to go into the parameters block. Now remember, parameters are the things that we want to see at the end. right? So when we go to print all this crazy stuff out, we're going to see the parameter values. And again, the parameters are the things that are going to be fit or estimated by the model. Note that theta j, right? So we have that bracket, square bracket notation. That means that we're going to have theta with j slots. J equals 4, so we're going to have 4 slots. The first slot is going to be vehicle, the second one is low, the third one is medium, the fourth one is high. And it works out that way because that was the ordering that we used for n, and that's the ordering that we used for y. If you decide to start swapping things around, moving them around, then you're going to break stuff. We don't want to break stuff because then stuff doesn't work. So keep everything in the same order, always, 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 always. This alpha here is going to be the alpha for all studies, and the beta is going to be the beta for all studies. So what's happening is we are actually, we have a hierarchical structure where we are basically saying that there's a global alpha and a global beta that is shared by vehicle, low, medium, and high. Got it? So what we're doing is we're saying there is this hierarchical structure to our data set such that we have these different levels of treatment: vehicle, medium, low, high. Sorry, I took that out of order. Let me try it again. Vehicle, low, medium, high. There we go. I got it right that time. And so there's going to be this global treatment effect, or global alpha and beta. They're going to influence the value of theta. So theta, which is what we actually care about, right? It's the thing right here. It's the thing right here. That is going to be figured out by alpha and beta, the two distributions for alpha and beta. Alpha and beta, like I said, are global for the model. So what this ends up doing is it ends up moving the different dose groups a little bit closer to the global mean of the system. So what does that mean? That means that if you're to take the binomial distribution for all this data and then calculate the mean, and then calculate the mean of means. So you start off with 4 means, one for each dose group, and then you calculate the mean of those means. That's the global mean. And if you have a lot of variance in a particular dose group, it's going to get heavily penalized to move towards that global mean. What that means in practice is that some of these values are going to, some of the theta values, the probabilities of tumor that we're going to get, are probably going to be different than if we didn't use a hierarchical model. Now, you might be saying to yourself, wait a second. You just told me that these might be different. Now, if they're different, does that mean that the models don't validate? And it depends on how different it ends up being. Generally, though, in a hierarchical model, we'll say that the model still validates if most of it's pretty close. What we're doing is we are understanding the concept that sometimes, and I shouldn't say sometimes, most of the time, when you use small sample sizes, you're going to get extremes. So you're going to get extreme sampling such that the mean or the variance might be a lot larger, or sometimes the mean is shifted way far away from the population. And that's where we're trying to shrink this all back and say, okay, that set of data that you have there for that particular dose is probably really wonky, and it needs to get shrunk a little bit. And because we're doing that shrinking, what we're doing, and assuming that it's just a little wonky, we end up making it so that we're less likely to find false positives, which is why Andrew Gelman, and I forget who he co-wrote this with, published a paper several years ago where he laid out the theoretical foundation to say, you know, when you do an ANOVA and then you do the post-hoc tests, and your post-hoc tests need to be correcting for the false or the family-wise error rate, And so we might do a Bonferroni correction, we might do a Tukey's, pick your favorite poison. What Gelman figured out theoretically is that when we do a hierarchical Bayes, because we are moderating the more extreme values, we are decreasing the likelihood of, he prefers to talk about type S and type M errors, which is type S is sign error, so saying something's a negative effect size when it's positive, positive when it's negative, or type M errors, which is going to be the magnitude. So saying that the effect size is larger than it really is. Because we're using hierarchical Bayes, it will tend to moderate some of those more extreme values and decrease the likelihood that we're actually going to end up seeing a false positive result. Thus, we don't need to do multiple test correction a la Bonferroni, a la Tukey's, a la, name your favorite one, right? So that's why anytime I'm looking at a situation where I have a multiple test correction or a multiple testing situation, I will almost always use a hierarchical Bayes model. This last section here is the generated quantities. This is the section that we're going to use to calculate the values that we're going to use for validating the model. So, having said all that, we are now going to run this. So one of the differences you'll see between Module 3 and Module 2 is we don't need to have two different code blocks running the stand models. So we don't need two different stand models. We don't need one for vehicle and treated. We can use one. And I changed some of the names, so cancer module 3.stand, obviously. But I'm calling this tumor data instead of vehicle data, and I'm calling this tumor fit instead of vehicle fit, treated fit. Otherwise, everything's pretty well the same. Nothing really changed here. And we can see that, you can see I have this little error here where I forgot to change it. So you get to watch me type for a few seconds. Tumor data. Ta-da! All right. So it's going to run. And there we go. So again, to interpret this, we've got theta. If you remember from just a few seconds ago, theta is our probability of a tumor being found in a particular animal. And this mean value is the mean for the overall distribution. Theta 1 is, say it with me, vehicle. Theta 2 is, say it with me, low dose. Theta 3 is, say it with me, medium dose. And theta 4 is high dose. Yay! So we've got the vehicle, the medium, or low, the medium here at 3, and the high dose here at 4. And we can see just looking at these means, you can see, ooh, wow, the high dose has a pretty high probability compared to vehicle. So this will be an interesting test. Whereas, medium or low, not that different from vehicle. So this will be interesting to keep going, right? Oh, and I didn't talk about the Y tildes. Oh gosh, these are fun. So this is the vehicle. Now remember, Y tilde is from a binomial distribution. So this is the number of animals we would expect based on theta 1 to develop tumors. And you can see we've got 6.46. And in our observation, we had 5 animals. So that's pretty close, right? That's not too bad. For low dose, we have 8 here. And low dose, we have 8. Hooray! For medium dose, we have 7.47, and here we have 7. That's pretty darn close, you ask me. But we've got 14 here, and 20 was what we observed. So this is, remember when I was talking about the shrinking, or the moderation is a better term, moderating. So what's happening is we're moderating what's happening at that high dose, and we're saying, that high dose might be extreme. The model's thinking it's probably closer to 14. Now I can tell you, if I had another high dose in here that, had, so if I had high dose and then I had extra high dose, and let's say that saw 22, this would likely not moderate as much, just so you're aware. Okay, so we did all that. I would say, and this is, I explain it here in great gory detail, so feel free to read it. But to me, I know that there was going to be moderation, especially on the high dose end. I was expecting that. And so, since I was expecting that, I'm not at all concerned about the fact that this came out to 14, given the fact that for vehicle, low, and medium, these are all pretty well spot on. So, I really don't have too many complaints. I think the model is validated based on our observations, and so we're going to move forward. We can now answer that first question, right? What is the probability that each dose, including vehicle, causes tumors? We are going to look at here for theta. So it's 11%, 14%, 13%, 24%. If you wanted to, you could also use the median instead, which all comes out to the same. I like to include the 95% credible interval. This is where the actual value, there's 95% chance that the actual value is going to be between, for vehicle, 5 and 18%, for low dose 7.1%, 6 and 20 for medium, and 16 to 34% for high. All right. So things are going pretty good. I'm pretty happy with everything. Again, here I'm explaining the hierarchical model and that moderation a little bit more. And I'm explaining why the moderation is good, and comparing it to what we might do with multiple testing situations and frequency stats. So now we want to test, are any of these treated groups different from vehicle? This line here is going to extract the high dose data. That's how you do it. So let me show you something that's kind of neat. The thetas in this case, because we've got theta 1, theta 2, theta 3, theta 4, are actually in a table. So when I do this, when I say extract tumor fit, come on, dollar theta, there it is. It's a table. I'm scrolling up to the top here. This is theta 1, this is theta 2, this is theta 3, this is theta 4. Now in R, if I want to get up the columns of a table, I'm going to use a special notation. And that's where this square bracket comes in. So it's going to be rows and columns. So you can see I've got dollar theta, and then because this is a data frame, or this even works for matrices, I can specify which row I want. I can specify which column I want. So if I wanted to get cell 1, 1, which is the first column the first row of the first column, I can do that. If instead I want to get, let's say, all of the first row, I could do that and leave the column blank. If I want to get all of the first column, I leave the row part blank and I put a 1 there, and this will give me the first column. And you can see it is huge, right? Because there should be 15,000 entries. So that's how we navigate that. So this part here says, grab me the fourth column. This one here says, grab me the third column, because that's where medium is. Low, grab me the second column. Vehicle, grab me the first column. So that's how we do that. Now I'm going to build a data frame. This is very similar to what we've done before because ggplot expects data frames. Making a data frame, and I'm going to have a column called theta, and we're going to concatenate together vehicle fit prob distro, so this one here, and then low fit, and then medium fit, and then high fit. We're also going to create another column called group, and group is going to have vehicle, low, medium, and high. And again, it's going to repeat vehicle the number of times that I've got length for this particular vector, and so on and so forth, right? So it's going to be vehicle repeated 15,000 times, then low repeated 15,000 times, then medium, and then high. And if you wanted to see what that looks like, that's going to be, let me run this just to make sure it's in memory. There we go. So TVDF looks like that. If you just want to see the first several rows of it, you could do head. If you want to see the bottom several, you could do tail. There you go. So we did all that, made this data frame, and now we're going to ggplot. So we're plotting this out. because it's a histogram, we specify the X value, which is theta. That is the data that we want to actually plot. We're going to color by group and we're going to fill by group. Otherwise, it looks kind of weird. Pardon my SQL update going on in the background. And you can see purple here is vehicle. This weird blue-green color is medium. Low is the green color. And then high is the red. All right. So what we see is, for the most part, vehicle, medium, low, they kind of look kind of overlappy. High is kind of hard to see what's going on, but high doesn't look quite as overlappy. So what we're going to do is, we've looked at this visually. There's something there. I personally probably wouldn't run the low and medium compared to vehicle comparisons, just because it doesn't look like it's going to be very fruitful. But I've been surprised, so I'll run them anyway. The high dose group, I think, appears to have a lot of its mass to the right of vehicle, so I'm more than happy to run that one. Yeah, this is what we're going to do. We're going to start off with the low. We're going to calculate the diff distro again. It's the low fit prob distro minus the vehicle fit prob distro, right? So it's just mathematical subtraction to get the low diff distro. We're going to get medium the same way. We're going to get high that way. So medium minus vehicle and then high minus vehicle. And then we're going to build this data frame. This is really simple, right? We're going to call it theta as the column. So theta is the column. And there's only one thing going in, low diff distro, so we don't need a group, right? We're going to run this. And there's our diff distro. Now look where 0 is. We have a lot of mass in the negative range. So 0 is definitely going to be a credible value in our 95% highest density interval. The rope is going to go to about here, so 0 to here. So it's a very narrow rope, but it's smack dab in the 95% highest density interval in my estimation. But hey, let's run it anyway and see. So we're going to use HDI, and here I'm using the print function, so to make sure that I get the HDI information out. And then I'm doing this. Ooh, I'm using paste. We haven't used paste before. Paste is a fun function. It allows you to mix text with reading out other objects as well. So I want to print a message that says low diff distro median colon, and then this is the median value. We're going to run it anyway. There we go. So what we see is the 95% highest density interval definitely goes negative. It goes out clear to negative. Well, I wrote 5%. I should have written 6%. Let's just update that real quick. So it goes down pretty quick, quite a ways, which means the rope is definitely squarely inside of this 95% highest density interval because it goes all the way up to 11%. So this range of 0 to 0.0001, which represents the 1 in 10,000 de minimis risk that risk assessors like to use for cancer, that's squarely within the 95% highest density interval. The way I apply my decision criteria, I would say that vehicle and the low dose group are not different from each other. Some people are going to differ with me, and their decision criteria are going to be to say that if the rope is smack dab in the middle, what you have is a situation where it's inconclusive. Now, unfortunately, based on my experience, I'd be calling most things in life inconclusive, and that's not really helpful. I don't buy into the idea that it's necessarily always inconclusive. I think in this particular case, with the low dose diff distro median being at around 3% or so, I don't really buy that that's going to be really inconclusive. To me, it's pretty conclusive that this is highly similar to vehicle. Is it identical? Of course not. It's never going to be identical, but it's going to be close enough that it's going to be very difficult for us to tell the difference. Now, the folks who would say that this is inconclusive are also going to have a problem with our rope. I also have a problem with this rope, because what they're going to say is, well, if you feel so strongly that 3% is no different from 0, then shouldn't your rope be wider? They are 100% correct. Our rope should be wider. So to me, a point estimate isn't that useful statistically because it has such a tiny probability, right? Because it's a point estimate. It's infinitesimally tiny. And so therefore the probability is infinitesimally tiny. We have these ranges so that we can actually calculate a probability. So I get it. I get when people say it's inconclusive. And their argument to me would be, well, the rope needs to be wider. Unfortunately, from a risk assessment standpoint, I have to use the rope that I'm given. Biologically speaking, this gets back to an issue of detection limits, right? So can I actually detect a 2% difference? Well, if I got 60 animals, right, we could do this real quick. 1 over 60, I can calculate, a 1.6% difference, because if one extra animal gets a tumor, that's 1 over 60. So theoretically, I could maybe arguably set the rope close to 2%, maybe 1.6%, and say, this is my rope. It's hard, and as toxicologists, we've never really agreed on what is biologically meaningful differences for hardly anything. In the clinical space, they certainly have, but in toxicology, doing animal studies, we have not. So if this were a human study, it'd be much easier for me to do this because clinically we have to, right? But like I said, with animal studies, we haven't really talked about this. So it's kind of hard to set the rope for a lot of things. That, is a philosophical discussion for another day. And maybe we will all have that and have fun. But for all my intents and purposes, I say that there is no evidence of an increased risk of tumors compared to vehicle at the low dose. And even the people who say that is inconclusive, they will agree with that sentence. So everyone will agree, all the Bayesians will agree, that there is no evidence of an increased risk of tumors compared to vehicle at the low dose. That is not debatable. So we can make that statement just fine. Medium looks a lot like what we saw with low. Again, it's a lot of the same explanation, a lot of the same stuff. So you can just read it yourself. Now let's go to the high. This is where things get interesting. So I look at this and it's like, okay, here's 0. The rope is probably here. Not much of this distribution is sitting within that rope. We might have a winner here. So we run the highest density interval. And now that's stretching from 2.8%, so let's call it 3%, out to 25%. Definitely the rope is not within that, right? Our median difference is around 13%. So I'm pretty sure I could say, yep, the high dose definitely different from vehicle. Now, those of you who are looking at Module 2, you're probably thinking, wait a second here. I mean, we had a much larger effect size there, right? The high diff distro median was much larger than 13%. And you're probably saying, but you didn't do a hierarchical Bayes when you did Module 2. And I'm going to say you're right. I didn't, because that's not my policy. My policy is that I only do a hierarchical Bayes when I have to. And those situations are going to be, as I lay out right here, when do I think you need to do a hierarchical Bayes? Under 2 conditions. 1, when the study design requires it. Or 2, when you're running into a multiple comparison situation. Outside of those situations, I really don't see the benefit of using the hierarchical Bayes. Now then, you're going to say to me, or you should say to me, now, but you just said earlier that we could be looking at some kind of, extreme effect. So why wouldn't you want to moderate it? Well, the issue becomes we're going to end up moderating the vehicle, which we did here, and the other dose without any other information available to us. And so my concern becomes if I have no other groups adding in information into the hierarchical model, I'm concerned that we're going to overdo it, over moderate, over penalize because of this lack of information. it is not uncommon for us in a, you know, treated versus vehicle situation where it's just one comparison to not run the hierarchical Bayes. And like I said, I think there's very good evidence for us not to do that. So that's where I fall on that particular issue. So I stand by the code we made for Module 2. That is how I handle that situation every single time. But when I have more information, because I am running a multiple comparison, I will run a hierarchical Bayes. I will also run a hierarchical Bayes if I have a 2-group comparison where the study design requires it. That is the only other time I'll run a hierarchical Bayes. So there you go. Hopefully this was informative for you. I think it would be very instructive and very useful for you to compare Cancer Module 3's code to Cancer Module 2. And pay attention to the differences and the similarities. For the generated quantities, one of the things that you will notice is that we have y tilde j. But we are not putting that on theta. And you might be wondering, why doesn't theta get a bracket j? And the reason why is because Stan does something amazingly confusing. Stan understands, because I put a tilde, or because I put a bracket j under y tilde, that I want it to run with the values of theta based on j. I know, it's confusing. The vector, this is what we call vectorization. The vectorization in Stan can get very confusing if you don't understand Stan that well. The good news is, for most of what you will want to do, you can always come back to the code that I've given you, or you can Google it and find what the solution is. If you run into a situation where you can't find it in Google, you run into a situation where you can't find the solution in the code I've given you, and you just don't know what it is, and when you run what you think the answer is and it looks not right, feel free to contact me and we can go through it. I've got consulting hours, coaching hours. That would I would consider that coaching hours. Coaching hours for me are at a much lower cost. I charge a lot less for coaching than I do for consulting. Consulting is where I actually do the work. Coaching is where I help you do the work. And I charge significantly less for coaching because I want people to come in for coaching. I'd also like your business and have me do the work too. Don't get me wrong, but I want to encourage people to come to me for coaching. So I do have coaching hours and coaching fees that we can talk about if that's something that you need. But like I said, for the most part, for what most toxicologists and pharmacologists run into, you can find it on Google, or you can find it in the code that we'll be going through. So keep that in mind. Anyway, like I said, review Cancer Module 3. Look at it, compare it to Cancer Module 2. Look for the similarities. Look for the differences. We have now gone through a very, very complicated multiple dose kind of cancer study situation, something you might find in a national toxicology program to your cancer bioassay report. This is the kind of data that's not uncommon. When I was at EPA that we would review. You find this all the time. So hopefully we've come to the end of the cancer modules. There will be some homework that you can work through to help reinforce some of these concepts so that you can practice on. And I encourage you, if you get done with the homework and you still want to practice is always good. You can come up with your own, crazy story problems like this one here, and you can run through it and you can see what you get. The code, thankfully, isn't really going to change, in terms of the Stan code. What's going to change maybe is some of this stuff might change, but a lot of it doesn't. And that's the beauty of the code. Once you write the code, you can go back and you can reuse it. Anyway, that was fun. At least I think it was fun. Hopefully you thought it was fun too. If you didn't think it was fun, I'm really sorry it was so painful for you. If you really, really hated this, trust me, please go back through it again, rewatch the video, go through this. If you still don't quite get it, reach out to me and we'll see if I can explain. I understand completely that this is pretty complicated, but I know you can do it, and I know you can do hard things. I know you're excited to get out there and learn. So anyway, I'm going to stop jabbering at this point. Go review the slides again or the video again, review the code, and hop into that homework. I'm looking forward to seeing what y'all can do. Thanks.